All right, so we've talked about functions, we talked about relations, we talked about domain and range. And while we were doing that, we were kind of relating back to linear relations, grade 9, 10 concepts. And then we talked a little bit about the grade 10 concept of a quadratic. So we're going to do a little more focus on quadratics and working with quadratics. We'll move through a few different types of functions this year, but about a third of our course focused around these quadratics. So quadratic functions, this should be some review, hopefully. Some of it might be brand new because every day is a new day. But let's take a look. Quadratic function is a function that has the form ax squared plus bx plus c, where a, b, and c belong to the real numbers. So as long as a, b, and c are some sort of numbers. And a is not 0. B and c can be 0. A has to be a non-zero number. Basically, a quadratic function has the highest power of x squared. So if I hide the a, bx plus c, not a function. That's a line. But if I hide the c, that will still graph as a quadratic. Sorry. Still, it's a function, not a quadratic function. And if I cover the bx, that's still a quadratic function. If I cover those, that's still a quadratic function. As long as the highest power of x is x squared, you got a quadratic function. When we graph it, what we see is a parabola, and that's that symmetrical U-shaped graph, opening up like a regular U, or opening down like in the diagram down here. This here is not a quadratic function. Why is that not a quadratic function? Well, simply put, vertical line test. Look at that, not a function. X value would have more than 1, so that not a function. Okay, that's bad. Some key values on the quadratic function. To recall, we'll do them in phases here, but we're going to start with the vertex and axis of symmetry. The vertex is the point where the parabola changes direction from up to down or down to up. So here we have a parabola, and we always read from left to right, just like we're reading text. So as we go from left to right, we're going up, 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 up. Stop. We're going up and we're going slower, 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 slower up, and then finally stop. And at this point, we actually have paused. We're not moving, and then we're going down, 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 down. So change in direction happened there at the vertex. Here we're going down, 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 down. Slower, 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 stop. And then start going up, 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 up. If you throw something in the air and you graph that, the height versus time, that point, there's a single point where it kind of just, it's instantaneous. It's not a nanosecond, it's smaller. It's just this single snapshot in time where it actually pauses before it starts coming back down. That's the vertex. The axis of symmetry is the line running vertically through the vertex, cutting the parabola into two symmetrical halves, meaning they're exactly the same. Now, my diagram might not be exactly the same because my drawing skills are not the best. But here, if you remember back to elementary school, if you use the red mirrors to do symmetry, you put the red mirror on the line, and then it would like make a mirror image of the object on the other side of the mirror when you look through the mirror. This is the same idea as the red mirror. This is the red mirror, gets set on this line. This parabola should match side by side. You should be able to take it, fold it in half through the vertex, and it will match up exactly. So let's take a look at some situations that involve quadratics, like maximizing the area of a rectangle. So when we want to maximize the area of a rectangle, we can look at some quadratics, because area is length times width. So meters times meters, feet times feet, centimeters times centimeters. It's a unit squared. Squared includes our quadratics. So let's take a look at this situation here where we have a city approves money to buy 100 meters of fencing to build a community garden. If the garden is rectangular in shape, what dimensions will give it the largest area? So we can use different sets of dimensions, and they'll give us different area values. We want to make sure that this garden gets the most area possible given the amount of fencing that it has. And we can see this, and we'll just do a little simple diagram here on the side. And it's nice that I got grid paper to do this. If I have, say, 4 meters of fencing, let's do more than 4. Let's do 8 meters of fencing. If I got 8 meters of fencing, I could have 1, 2, 3, 4, 5, 6, 7, 8 meters of fencing. That's 3 squares. So 8 meters of fencing is going to give me 3 squares. But if I have 8 meters of fencing and I do 1, 2, 3, 4, 5, 6, 7, 8, look at that, different shape, and all of a sudden I got more area. This same 8 meters of fencing got me more area between these two. So depending on the shape we use, different dimensions will give us different areas. So let's take a look at this, and we'll break this down to 100. So we'll just break it down by tens. Seems nice. So we'll do length, do width, and then the area. So the length and the width have to add up to half of 100. Why? That seems weird. Why wouldn't they add up to 100? Why only half of 100? Well, here's 8 meters of fencing. The length and the width, there's 2 widths, there's 2 lengths, so half of it only hits half the rectangle. Length and width, it's only half the rectangle. So the width and length have to add up to 4 in this case, even though we had 8 meters of fencing. So in this case, the length and width have to add up to half of 100. So if the length is 0, then the width would be 50. If the length is 10, the width would be 40. If the length is 20, the width would be 30. If the width is, the length is 30, then the width would be 20. And if the length is 40, the width would be 10. And if the length is 50, the width would be 0. So those are based on using 10, and there's some values probably in between that we could use. But using those, just using 10 so that we don't have to make all 100 different situations. Let's kind of start taking a look at where we're at. So area is length times width, right? So we take length times width, that equals area. So let's look at all our different areas here. This is kind of our T-chart. 0 times 50 is 0. 10 times 40 is 400. 20 times 30 is going to give us 600. 600. 400 and 0. So there we have our different areas. And we can see these seem to be giving us the largest dimensions. Now, if we were to plot this, what we're going to see, and I'm just going to do, what do we got, 10, 20, 30, 40, 50, and then some hundreds here, so we'll do 200, 400, 600. Just a small little graph to kind of show us what's going on here. We got, now this is going to be our length and area. We're going to compare length and area. So these are hundreds. We can't graph all 3, so we're just going to pick one of the dimensions. If we know the length is 0, then the width has to be 50. It's given, and so that these are the calculations. So we're going to compare length and we're going to compare area. So length and area. We can conversely do width and area. It's going to give us the same graph. So we have 50, or sorry, 0 length. It's going to give us 50. So that's going to be like a quarter down here. Or no, sorry, it's going to be 0, 0 and 0. And then 10 and 400. That's right here. And then 20 and 600, right here. And then 30 and 600. And 40 and and then 50 and 0. We kind of look at that, and it kind of looks like a parabola. My drawing's terrible, by the way. Kind of looks like a parabola. I'm thinking that somewhere in between here, that's going to be our maximum value. Like, right in between, maybe? And so let's kind of take this, and we're going to switch over to Desmos. So Desmos, if you don't know, is an online graphic calculator and graphing application. It's just desmos.com. Okay. You can make an account, which is convenient because you can go back to your work as you use it. But let's just use the graphing calculator here. Yeah, and you can log in, sign up, and all that. But we can do a couple things here. We can make a table. So I'm going to do table. And we'll do the same table, actually. So we got length, do length, the widths, and then the areas. And I'm just going to turn width off. I don't want to graph the width. So our different lengths were 0, 10, and then it's smart enough to realize the numbers there for me. And then this is 50, 40, 30. Actually, let's do a calculation here. 50 minus L. Does that work? No. Okay, it doesn't work. Never mind. Oh, width is 50 minus L. That's where it goes. Look at that. It fills it all in for me. And then the area is length times the width, which is 50 minus L. Boom. Look at that. Same table. Filled it all in for me automatically. You only see one point here because, well, my scale's not big enough. I got to get the length going up to 50, and then I'm going to not graph those ones. And then I got to get the area here. This part's the area. Up to 600-ish or more. So I'm just going to hit the graph settings, and I'm going to set the x-axis from, I usually do like -10. I just give it a little bit of space on the end this is the L values. The x-axis is the L value, so I got to get up to 50. So I'm going to just do 60. Okay, so there we go. We got our two endpoints. And then the y value needs to go from, and again, I just like to put a -10 in there. Just give it a little bit of space. Up to, so we had 600. We want to go a little bit higher. Let's go up to like 800. Look at that. Okay. So we got this going on here. If we look at this formula here that we calculated the area with, which was the length and 50 times the length, that's like actually, we're going to put a new expression in. If we expand that, 50L minus L squared. Right? We just multiply both of those as we expand. So we got 50L minus, we'll do our A equals 50L minus, I'm having trouble typing here, minus L squared. And I think we got to change these to x and y on here. So A would be our y value. Oh, there we go. And then this is our x value. There we go. Look at that. Oh, there we go. Beautiful. We got our graph. And look at this graph. So that's we just expanded the length times the width, and we said the width was 50 minus L, which it is. And there's our graph right there. And we can see that we have, and this is beautiful on here because it snaps right to the vertex. Look at that, 25 and 625. That's our maximum value for the area, and it happens when the length is 25, which means the width is 25. So let's switch back here to our note. So this point here, which happens right in between 20 and 30, which is going to be 25, and works out to 625. The vertex of the parabola is the highest point. So what are the dimensions that give the largest area? Since the vertex gives the max value for area, the dimensions are 25 by 25 for a 625 meters squared rectangle, which happens to be a square. Note, maximizing area, always going to be a square. So since we're just comparing the one dimension to the area, vertex ends up being the point where the area is maximized when the perimeter is fixed. Okay, a little bit more here. We're identifying quadratics. Quadratics can be identified in a variety of ways. If the graph is a parabola, it's quadratic. If the highest power on the x in the equation is x squared, it's quadratic. This might require simplification, like if you had like the situation we had where we had x and then 50 minus x, right? That was our area formula. We had to actually expand that out, simplify that, so we had 50x minus x squared. That's our highest power. So sometimes you might have to expand it out to simplify. And then the third case is that if the second differences on the table of values are equal, then we know it's quadratic. And we'll take a look at that. Are the following values linear, quadratic, or neither? Well, highest power of x, we got an equation. Highest power on x is just a 1. That's a 1 there, technically. So that is linear. In this case here, we got x squared. That's good. Wait a minute. We got an x to the power of 21. So that is neither linear nor quadratic. Moving on to the next one. Oh, look, we got an x squared. That's quadratic, right? Wait, but it's on the bottom. Does that mean anything? Yeah, it does. Because if it's on the bottom, then it's technically equal to 2x to the negative 2. Negative 2 is not x squared. That is x to the negative 2. So that is neither. Why am I putting a g in there? I don't know. Neither. Okay, so no quadratics in our equations. A couple look like it, but they were a little tricky. What have we got a table of values here? Okay, so we got a few table of values to work with. So now, when we had the table of values, we got to have the second differences being the same. So that means we got to make an extra column. And we'll make the first differences. And when we do the first differences, what we do, oftentimes it's easy sometimes to make a little chart like that. We ignore this first box, and we do the difference from 6 to 8. So going from 6 to 8, that's plus 2. Going from 8 to 10 is a plus 2. 10 to 12 is a plus 2. And 12 to 14 is a plus 2. The first difference is the same. Yes, the second, third, fourth, fifth, and 57th millionth differences will be the same, because afterwards they're just zeros. If there's zeros, it doesn't count. They have to be some non-zero value. Here, the first difference is the same. This one's linear. That's going to make a line when you graph it. And you can try that out. Plot it into Desmos, and you can check that out. You'll see it's a line. In the next case, we'll try the same process here. So the first differences. So again, make the box. You don't have to make the boxes, as long as you stay organized. But so we're going here from 1 to 2. We're going up 1. and then we're going up 3, then we're going up 5, and then we're going up 7. Okay, first differences aren't the same. So we keep going because we're looking for the second difference to be the same if it's quadratic. So we can cancel out that first box and the second box now. So now we'll just look at this set of numbers here. Going from 1 to 3, positive 1 to positive 3, that's a plus 2. That's a plus 2. That's a plus 2. Well, look at that. That's quadratic. So we finally got a quadratic. Took us 5 tries. All right, let's take a look at the last one here. Okay, they got a kind of neat pattern here, looking maybe positive. Quadratic kind of have that repeating pattern. So we'll try it out. First difference is block. So with that first one, 27 to 1. Okay, so that's going to be negative 26. And then that's going to be 0. And then that's going to be plus 26. And then that's going to be, geez, that's a 98. Going up 98. Well, let's check our second differences. See what happens. All right, negative 26 to 0, so that's an increase of 26. That's an increase of 26. Looking good. Oh, geez, that's an increase of 72. That's a fail. That is not linear, nor is it quadratic. That is neither. I probably would guess that's going to be a mess. I don't even know what that is. I just made that up. So that's neither. So when we're identifying quadratics, again, as long as you got a parabola, it's quadratic. Highest power on x is a 2, quadratic. And then if the second differences on the table are the same, it's quadratic. And that's how you can identify a quadratic equation.